Today, I will present our feasibility journey of testing over-the-counter products with multiple APIs using Expo's FFSim. So the storyline was we were supposed to evaluate continuous manufacturing opportunities for consumer health. So our management came up and said, yeah, let's check over-the-counter products and the subsequent business cases to be switched to continuous manufacturing. As an expert, you think, yeah, what a wonderful challenge. So management says, I have a product in mind. And you think, yes, let's start simple. Use a product with one API in high concentration and a simple process. Management has a different idea. Regulatory-wise, this one is easy. It's a monograph, MIDLE. So monograph does not have the same regulatory implications as a dossier. And you as an expert think, what? But you say, nah, can be challenging as we do not know if the census can track all three APIs. But management is convinced, no problem, I'm sure you will make it work. As a disclaimer, the plot is entirely fictional. Any resemblance to real persons or events is purely coincidental. So what is MIDLE? MIDLE is an over-the-counter medication primarily used to relieve symptoms associated with menstrual and premenstrual syndromes. It combines active ingredients that are designed to target various symptoms. We have paracetamol in a concentration of roughly 77 weight percent, caffeine around 9 weight percent, and pyrilamine maleate with 2.3. And we wanted to test NIR spectroscopy for blend uniformity measurements. Primarily tests or primary testing with NIR and Römer offline showed that there's a low probability to detect pyrilamine in the presence of that high amount of paracetamol in a static bed. So we couldn't find any correlation. So we went into brainstorming with a team and decided it may be worth testing in a moving bed. And we were thinking of how can we do that with low effort and high gain of information. So we came up with the feed frame simulator of Expo, and we wanted to test different formulations. On the one hand side, granulated APAP or powdered APAP, which is the paracetamol. And on the other hand, we wanted to test NIR and Römer at once. So we started off with a design of experiment and went into the trials, which we performed in Cork, Ireland, same building as our user group meeting is in. Here you can see our arrival, the setup, and Matthias, my colleague, and Phil measuring with the NIR and the Römer system. So the setup of the trials for proof of concept was as follows. We were testing powdered APAP versus granulated APAP. The granulated APAP contains povidone, which is a good Raman scatterer. So we were hoping that actually that can be used to improve traceability of our pyrilamine if we use powdered APAP and combine povidone in a pre-blend together with pyrilamine maleate. So instead of having our povidone within the granulated APAP, we use it as a tracer for in a pre-blend with our pyrilamine. So in the end, we had two different formulations, and we did a DOE of each formulation. Caffeine and pyrilamine were varied over 5 levels, and APAP and everything else was used as a filler. These are the variations that were used. So from 58 to 133% label claim was the variation region of caffeine, and for pyrrolymine it was a little lower, so it was 78, 124%, and then the rest was varied accordingly to fill up to the tablet, to the 100% tablet weight. The experimental setup included a centronic centropod, and we were actually also using our own Raman system, but for that, Jens will present the results a little later on. So this is the setup. We had a small scale blend production. We were focusing here now on granulated APAP due to the later tested tableting results. So what did we do? We did dispensing and blending. We did additional blending. Apparently, a feed frame is a good blending equipment, huh? And then the measurement in the feed frame simulator. We took the blends and used it on a style 1 nano to get tablets out, and then we tested the tablets in terms of physical characterization. So, for example, main compression pressure and tensile strength. And additionally, we also gave it into reference analysis using HPSC. So what we've seen is, and that is also the reason why we concentrated on the granulated APAP, that the pure APAP, so the powdered one, you can see it here, actually has tendency to cap. So the tablets were actually more or less disintegrating when you had a stronger look at it. So the first step was the selection of paddle speed. We tried from 10 RPM to 50 RPM. And we did the same pre-processing for all the different models that we tested. The first pre-processing step is wavelength selection. The second, Savitsky-Goulet second derivative, 21-point smoothing, and then subsequently an SMB correction. Cross-validation procedure was always the same. We used vanadium blinds with 24 to 34 splits, 10 samples per split, and we try to align it because apparently there's a varying amount of spectra depending on the RPMs that you're using to have the same ratio that is taken out from our during our cross validation. So here you can see actually APAP with our root mean square error of calibration and cross validation, and there's barely anything that impacts APAP. So it doesn't matter whether you go slow or fast, it always nearly stays the same. It's already quite different for caffeine. So you can see actually that the optimum with the lowest root mean square error of calibration and cross validation is with 40. And then it increases slightly when we come to 50 RPM. But the greatest impact is, and that is having a look at the concentration that pyrrolymine is in the tablet, is the feedback from pyrrolymine. Here, the root mean square error of calibration and cross-validation change dramatically in dependency of our pedal speed. So in the end, we selected the highest pedal speed that we had, at 50 RPM, and continued optimizing on that. So our APAP model, and we just roughly combined all the 6 latent variables that were proposed. So with a 50 RPM, this is the concentration of the respective DOE trials, and you can see here the root mean square of calibration and cross-validation is very low with 0.2%. And you can see here in the scores plot, I usually like to present it color-coded because that is the easiest way to get that the information of what a scores plot means transferred to anyone who's not into PAT and multivariate data analysis. So I've tested it. It's even management applicable. And you can see here quite nicely that here is an increase of, this is the direction of increase of APAP concentration. The DOE4, which is the 100% standard combination, is nicely situated in the center. And if we move forward to our caffeine model, we have here an error of 1.6, and for cross-validation, just slightly higher. So also that is quite nice. But our caffeine model, and this is quite interesting, is not entirely independent of APAP. So we can see latent variable scores on latent variable 1 showing the APAP increase. And if we combine it with the scores of latent variable 3, we can see this is the direction of the caffeine concentration increase. For pyrilamine maleate, and this is quite a nice feedback that we got during the trials, we also had the 6 latent variables. We have a root mean square error of calibration of 2.8, and cross-validation is around 3%, which is actually really good. And what's most interesting is actually that our pyrilamine maleate model, despite the fact that there's so much APAP in that formulation and also a lot of caffeine, this is entirely independent, more or less entirely independent of caffeine and APAP concentration change. So this is the direction of the pyrilamine concentration increase, and that is scores on latent variable 2 and scores on latent variable 3. And if we take the same latent variables and check the scores plot for APAP, color-coded by APAP, you do not see any trend here, similarly to caffeine. So this altogether looks quite promising. We can also have a look at the pre-processed data, color-coded by concentration changes of the respective APIs. And our APAP concentration increase goes from dark blue to light yellow, and you can see there are numerous of peaks that can assigned to the concentration change of APAP. There's also quite some opportunity to check the concentration changes of caffeine. I noted some of them. They are in the range between 1,300 to 1,500 nanometer. And if you take a look at this pre-processed spectra color-coded by the concentration changes of pyrilamine maleate, it's much more difficult. So this is one of the wavelength regions where you do see some of these changes. It goes from roughly 1,200 to 1,300 nanometers, and you can see here that there are some signs where you can actually get information on the concentration changes of pyrilamine. So the conclusion, we are back with our results at our management, and they asked, how did it go? Well, much better than expected. We managed to test in only 2 days if either NIR or Römer can detect all three APIs. So that's fast. What was the outcome? Both spectroscopic methods work fine. We may need a little optimization, and then we can test it on the existing continuous manufacturing line. I told you it will work. So Meike will be running on the CM line in 3 months then? What? So we went into transfer and had the first check on the Conti rig. This was the know-how transfer. So what we actually figured out during this feasibility, the first proof of concept, was that we need to ensure independency of the three APIs and the maximum possible concentration variations for APAP. So that required that we combine two DOEs. We have an outer DOE, which changes the APAP concentration or focuses on APAP concentration, and around the center points of that APAP DOE, we included a DOE focusing on caffeine and pyrrolidine concentration changes. So the DOEs were tested using NIR sensors in the feed frame of a standard tablet press. The preliminary models which were obtained supported the process development. The obtained tablets were analyzed with HPLC, and our current formulation is actually using a different formula as the process uses wet granulation. So it was really helpful to have already an existing model which at least shows you tendencies, whether you're improving or your process gets worse. So continuous process with theoretical Meike formulation is currently tested on the existing continuous manufacturing line at Bayer. What was the outcome? So in our first trial, we checked blend uniformity with online measurements, with a preliminary model, and we did a step change of paracetamol from 100% label claim to 70% label claim. You can see it here. So this is the axis for the APAP concentration change. And you can see nicely that it converts from 100 to 70%. The concentration change for pyrrolidine and caffeine is noted on that axis. And caffeine goes from 100% label claim to 280%. That's the orange line. Pyrrolidine maleate is the same range, and it's the green line. We did have some unexpected process stop, but nevertheless, we could see quite nicely that the preliminary model already follows the trend. In reality, we had actually 104 to 280 for caffeine and roughly 97 to 295% label claim change for pyrrolidine. So what is my outcome? I think we need a change of paradigm here. Process development and formulation development are usually based solely on quality target product profile. But I think the quality target product profile is not the only factor that actually should impact future formulation development. Currently, it runs like that. We have API properties. We have a quality target product profile. According to that, we define a formulation. Based on that formulation, together with the process is further developed. We have in-process controls, then set up later. We have release analytics in the QC lab. And this is more or less a stepwise approach. But if continuous process and measurement is targeted, the sensor can have an impact. So what we actually should do when we have a formulation in mind, we should check feasibility on sensor and determine the sensor choice. We may, depending on that sensor, and the choice of sensor available need to tweak the formulation. For example, there are excipients which have negative impact on spectral detection limit and may be exchanged. We also can have APIs with low concentration or limited spectral features that can be blended with a tracer or used in an active powder blend, and we just monitor the carrier. So if you have then defined your formulation and your sensor, which is going to track your formulation, you will develop the process, and together with the process, the control strategy. And also that is an iterative process. So altogether, the control strategy should be developed together with the process, and it should be based on solid understanding of process and respective risks. So for me, the control strategy constraints have a major impact. Thank you.